Okay. Yeah, so the things that I wanted to chat about today is maybe just go through a bit of where the simulation class is. I implemented the frequency domain code, or a new frequency domain code on top of the simulation. And I was thinking one of the things that we could do is just like download a notebook and like walk through what kind of user-facing changes are needed, and then maybe talk a little bit about what's under the hood. Yeah, are there other things you guys want to put on the list on the docket for today?
Well, I did the review yesterday for the PF review, and I'm getting one last 2.7 error on the Travis, and I'll have 2.7, so I don't know if you could handle it.
Okay.
It's not to me now, but if someone could handle it, 2.7.
Okay. We can take a look at that. And
yeah, I haven't updated too much because right before the vacation, but yeah, I have pushed some tools up there to play around with.
Cool.
We can just go through it.
Yeah, I mean, if you could give us just a bit of a tour of what's there. And,
okay.
Yeah, that'd be awesome.
I just have the brute stacking right now, but I almost got. I was working on it now that I'm reworking through the fast version, or like my really good one. I'm like, oh, maybe I'll try this. So I'm kind of diddy-daddling, sorry.
No, that is, refactoring is always a good place to do that. And I've been doing that a little in the EM code. I'm trying to like be careful about that because I still want to make it not too painful, but there's a lot of naming things that I look at and it just drives me crazy. But I'm gonna leave most of them for now. Okay, so I'll download, so this is one of the notebooks we prepped for the disk. And so this is the sounding over a sphere. Uses the frequency domain code. So we'll just take that and put it on the new one. And we'll just walk through like what's changed and maybe some of the, I guess, design philosophy in there. Yeah. So we don't need to install SimPEG. So here, right now, how I have things is the new FDEM package, because I wanted to be able to compare them both. So right now I have new FDEM, and I'm going to import that as FDEM. What we'll do, once it's sort of stabilized and I've put all of the examples on the new FDEM code, all we'll do is rename it so that new FDEM is now FDEM, and the other one is old FDEM. And we'll maybe give people like one version to sort of get off the old, and then delete that code. Cool, so we will import the new FDEM. Okay. So none of this is changing, this is just for Python. So we were setting up a frequency domain. We've got a source, a sphere, and a receiver, and then we're gonna do a frequency sweep. So nothing's changed with the mesh, of course. Here. I changed the color, but that's on just the SIL mesh branch, but just so that our colors are on like the Matplotlib updated ones instead of like the bright blue. So totally a style thing. Okay, so this is where things actually start to change a little. This code actually doesn't need to change because I used keywords for everything already. But right now, so in the past, we actually had sort of a separation between what are the arguments and what are the keyword arguments. And with this, I'm shifting much more towards putting everything on keyword arguments. And why we want to potentially do that is that it allows you to develop or build each object in sort of an order that makes sense. So for example, if here I was wanting to set this up and didn't actually have the orientation ready or anything like that, you could create it and it would be sort of like an invalid object in the sense that it can't actually compute data yet, but you can construct it as you go. So you don't, and we'll have a validation step on that so that when you actually go and try and use it, and like if you haven't set the orientation, you'll get an error that says, I need you to set the orientation before I can use you. So So this is also one thing where the names then matter again. Sorry. So if we're shifting towards using keyword arguments, that also then means that like our keywords need to be meaningful. So in a lot of places we were using a lot of shorthand. I think we should try and get away from that, especially as we're trying to get SimPEG adopted like outside. Shorthand to us doesn't necessarily translate, especially if people are speaking a different language. Yeah, so like lokes, I think should just be locations. But what we'll do, and I've done this with the solver, for example. So like we used to have solver as capital S. So I'll still let you set that, and I'll still let you call it, but we'll throw a warning for now. And so we can do that with things like lokes or whatever. We'll let you set it, but we'll say, don't do that. Do this instead. And then slowly sort of clear out those types of things. Because I think it's enough to sort of already change the interface a bit. I don't want to like change all of the keywords on you, because that would just be super annoying. So we'll try and make that as painless as possible.
How do you do it in the back end? You just look for lokes and location and just grab whatever.
So I'll show you what I did for the solver, which I believe is in the base. Okay, so here is the solver that I want you to set. And then what I've done here is I've got a solver like this. And so it's a property. And as soon as you call it, it throws a warning and says, use this one instead. Right now I'm raising an exception because I was trying to find where in the old code I was still using this. But then it'll return the solver. So that should be there, but it'll just return the solver. And then here on the setter, we'll do the same thing. So it says, don't use this, but then we'll still set it. And the same thing for the solver ops. So that will hopefully make it a little less painful.
Less painful is such a good term, isn't it? It's like, oh, this is not going to hurt too much. Okay, this is also going to make it less painful. Okay, Gangha Fat Choi. Is this totally disruptive of this?
No, just slightly. It's good. It's a good disruption.
Okay, so we have. You gonna explain all these things?
Actually, I don't know with all this old Chinese.
It's
Sure, yeah, like, what is this? Like, that's one Oriental, they're all the same.
It's gotta be, yeah.
Okay, so this is mooncake.
Okay.
Like the traditional New Year stuff for Chinese, I guess. And then this is mochi. I think all of them are mochi, but different kinds. I'm not sure
What's
what
mochi?
exactly is.
One kind of reminds me of a Twinkie.
I know, I'm sorry. Show up late, disrupt everything. It's like,
made of rice.
Okay,
it's
sorry.
a rice one. It's a rice flour and this. You mix in water and there's stuff something inside.
This is going to be the best one, I can tell.
Purple the best.
Taro.
Taro.
Go ahead, Dequan.
I think red is the best.
Dequan! Oh, you can tell us what
Here we go.
No.
What's this?
I can't see it. Too far.
It's too far.
It's a coffee. Food.
Goodies.
Yeah. Oh, it's red bean.
We don't know. And you're a Chinese.
I gotta try one of these.
Oh, that's my red bean.
Roll.
Roll.
100.
This is mango
This
milk.
one's really good, but the texture's.
Why? Birthday or what's the occasion?
Well,
here?
it's Happy New Year. What did you do for New Year's?
Oh,
What do you mean? You forgot already just because you're in the States? Trump doesn't celebrate Chinese New Year?
no, nobody celebrates Chinese New Year here.
Oh, wow.
We're celebrating the Winter Olympics.
Ah. Hey, great. That's a cool picture. Where did you dig that one up?
You mean my camera or?
Yeah. Oh.
Actually, I don't know. I didn't set it
Getting a
up.
lot-
I don't know where it's from.
A lot of good-looking girls
Yeah.
sending you.
Yeah, it could be from my wedding photos. Yeah.
Sorry, Lindsay.
For some reason, I just can't turn on my camera. It shows my camera not working. I don't know why. Yeah, weird. Everything's fine, but just there's no camera working on. So, yeah.
Okay, that's all right.
Yeah, I can see you guys.
Perfect. Yeah, I will switch back to sharing my screen. Can you see that, fine?
Yes, good.
Where were we?
Yes. So,
Dog.
I guess I missed out. Also, I was looking for the channel link in the channel meeting, and then I realized it's in general. Okay.
So we were just chatting through upgrading the code to simulation. So going towards using keyword arguments for everything. Did you guys read here for that? Trying to use keyword arguments because it then allows you to construct the object in a much more flexible way. So especially when you're thinking about the simulation in particular, like maybe you want to create the survey and then design a mesh based on your survey, or maybe you want to create a mesh and then from that create a survey, like whatever, we want to give you that flexibility. And so it's a lot easier to do that if we're setting stuff through keyword arguments rather than saying like when you instantiate the class, we need these things. So yeah, and then what we'll do is put a validation interface that then basically just says like before you try and use this thing, if you haven't set a mesh and we need a mesh to solve your forward simulation, like we'll throw an error, a meaningful error. And then we talked about just now, if we're using keyword arguments, that then means we need to be very clear with what those keywords are. So things like lokes, I'm not particularly a fan of, just because it's not necessarily all that clear. So we'll start moving that towards locations and just spell out the English word. But we'll do that in a way that lets you sort of set these things and throws a warning. So this will have changed. So we have our receivers. So here we now actually, each of these is going in as a keyword argument, which they're the same keyword arguments we were using in the past. So that'll be a bit of a step that you'll have to update in any of your codes. Okay, then here we no longer have a problem. We'll have the simulation. And then here we set the solver to solver. And then here, I'll run this and I'll show you what happens. Oops. Here. Okay, so we needed him to give the keyword mesh. And then what else do we need? We need the keyword for source list. Okay. So now that we have the keyword set, I do this problem.pair step like every forward simulation code is going to have in it. And right now I actually let you do that. So what we've done is I've put on the simulation a pair method that all it's going to do is say, like, I'll show it to you. It just says, yeah. So pair here is just then self.survey survey. So what I'll show you from the top level what you could do instead. So here we could have done then we had set the survey first. So let's say, for example, I did this. Then I could set the survey in here. That would be the same thing. Or if we had the same order as before, I could just instead do frog.survey. All of those three things are the same thing. So, but we'll lean towards the latter two and get rid of that pair step. But it'll be helpful in sort of getting your code up and running again, and then you can sort of like, once it runs, then deal with the warnings. And then here, problem has fields as it did before. So all of this code, nothing should have changed. Same here, nothing's changed. This will have changed. So the survey no longer has dpred, it's now the simulation, which I call the problem, based on our old naming. And so then that will be fine. Yeah. So that is the gist of that.
So just one quick. So under the new framework, the simulation is only the PDE solving, and the problem actually includes the how we measure the data, or like the predicted or observed data. Is that right?
Not quite. So we actually, there's a bit of confusion going on, I think, in this notebook because we're still using the word problem. In the new framework, the problem is gone. That no longer means it.
Okay.
So we have the simulation, and that does everything that the problem used to do, but now it actually has the survey as a property of that class.
Okay.
And so the survey class has been lightened significantly from what it was before. It used to be able to compute data and things like that. Now it doesn't. It just its sources and receivers.
Okay, now it's just a survey and a simulation.
Yeah.
Okay.
Yeah.
So where's data here?
So data is actually, this is something interesting. And so data is actually been teased apart from the survey. So data is its own object. It takes a survey. I'll show you the class actually. And so what we've tried to do here is actually sort of elevate the data in a sense. So here we've got our data class, we've got deobs. And when we have a true data class, what we're going to do is once you set deobs, not allow you to change it. And this is something we can debate, but I think that like once your deobs is set, we can take actions on it, and you can sort of choose, you know, I only want to invert this subset of data, like that's all fine. But I think that sort of once you get to this step, your observed data is your observed data. And if you want to do some sort of filtering or something before you invert it, like just make a new data object. Yeah. And then what we have done to allow a bit of flexibility is I've also then created a synthetic data object, and we do then let you can go in and change your data or your observed data for that. So where this changes things is the data misfit. So the data misfit will now take a data object and a simulation. Whereas before it used to take a survey, because the survey used to know about the data. But so we sort of reversed, if that makes sense, we've reversed the role of survey and data. Data is now like more important than survey. Data is the class, and it has the survey as a property. And then the simulation is a class, and it has the survey as a property. So if you're going to set up an inversion, you'll give the survey to both of those pieces.
So then you do a forward modeling, then does the predicted data that comes out, is that part of the simulation class, or does that get made into its own data object?
Predicted data is just a vector.
So it's just
vector of numbers.
So it's just part of the simulation.
Yeah.
It's like a property of the simulation.
Method, the simulation. It's not a property.
It doesn't really count as data. Like we don't think of it as the same way.
Yeah. So dpred is just a vector, always just a vector. What you can do on the simulation class is we do have the make synthetic data. Because we've used that in a lot of places. And so this will give you back a data object. So then if you wanted to actually do a synthetic conversion, this is what you want to work with. So here we have our clean data is just going to do self.dpred. So that gives you a vector of numbers that are your data. We set that, if we want noise here, we add noise and then set that as our deobs. and then I give you back a synthetic data object with diobs. On the synthetic data, I thought it might be handy just to store the clean data as well. You don't have to, but it's there. Then it takes the survey and the standard deviation. And so this will give you back something that then an inversion can operate on.
Sure, so you know what's the link between survey and data? It's the indexing, I guess, but not survey.
So here, the survey is actually a property on the, oops, sorry, that's the simulation. Survey is a property on the data class. So it has to, you need to add the survey to your data class.
But how are they talking?
Oh, you have to do like data.survey equals survey.
No, I mean, how is survey used? Where is survey used in your data class?
Okay, so survey is used to basically allow us to sanely index your observed data. So your observed data is just a vector of numbers, and the order of those numbers depends on where your sources and receivers are. So what we do is actually build this is all under the hood, but what we do is we build a dictionary of indices based on your source. So your survey has a source list, and each source has a receiver list. Okay. So we're going to go through, and for each source in the survey, we're going to look at every receiver and just say, okay, what indices in diobs correspond to you, and store those. So then here you can, on the outside, actually access the data like a dictionary. So you can do data of source, comma, receiver, and get back the data corresponding to that receiver, that datum. And so that's all done just by keeping track of what indices are associated with each source receiver. Does that make sense? And then we can use the same thing to index like uncertainties and stuff like that.
The assumption will be right now is just stack. The order is just source receivers.
Yeah, so the order is always like source, and then we'll go through the receiver list, source 2, go through the receiver list. Yeah. Yeah. Okay.
How flexible is the data class? Like what kind of fields can it actually contain? Is it limited, like the only data that the data class, can it only take diobs and an uncertainty? Is that all you can have in it? So like let's say like for the DC data, you go out and like there's really like 8 to 10 different things that they oftentimes measure for single like measurements. You might have your injection current, you might have your transmitter voltage, you might have self-potential, or like, so you might have all these different things that are measured at the same time, or we might have like the index of each of your different electrodes that are being used. You might have the index of your FDEM and N electrodes. Is there any way that we can add any of those other parameters to the data class so that when we're going through, like, we wanted to get all of the parameters that were associated with transmitter 5 and measurement 23, that we could kind of do that since we already have that dictionary set up?
Yeah, so that would require a little extra implementation. But I'll show you a simple example that might give you a bit of an idea. So what I did on the frequency domain class, this is actually new. So we didn't previously have sort of a frequency domain data object, but now we do. And so it's very simple, but there's a couple things that are just sort of handy. And so perhaps you want to get, which frequencies are in my data. Or if you have named transmitters or stuff like that, we can start to, like, you can inherit this class and then add what you need for that survey. So, yeah, so like the core survey will stay, or sorry, the core data object will stay lightweight, but then for each different type of physical survey that we think of, we can start to add some useful utilities to that.
How about like so what is it aimed for? Because let's say you have some ion and you need to read in like diastase, for instance, and like, do you want to put that in the data class or the survey class? Where, like, how are you actually parsing that out? Because so there's two things. Let's say all the information that Mike said is actually in that, like, a file outside.
Yeah.
You're gonna read in all those information. Some of them are going to consider as absolute data, but there are other pieces that might be useful.
Yeah.
So it could be a supplementary data. And well, I think so. Where do you think when, like, how are we going to parse that out? Like, so let's say we got an IO, we can somehow read in.
Yeah.
It's fine. The first question, okay, how, like, do we want to put the IO in the data class?
I don't think so. So, and this is something we should talk about, but like my take on that is that the IO should be separate, and it's actually like a utility or a parser type package, because each one, like every file format is going to be custom, and so I don't want to bog down like a data class with everybody's different file formats.
Right.
But to have a utils dot read DS and then bring that in and give you a survey object, a data object. That's probably it. I think that would be.
I kind of started on something like that where it was just, the utility would spit out what you guys need for the inversion kind of thing. So you would tell it whatever parameter you wanted. So. Yeah,
so basically what Mike suggested, like there was additional stuff actually like happening in the utilities or other IOs. And we can read in like kind of analysis on that part. We're not going to use a data class, rather we're going to use something different.
Yeah.
So you want to keep the data class a bit more simple, like basically observe data, application of the survey.
Yeah. And I think it's totally fine to think about bringing in if there is supplementary data that's useful, or if there's utilities on how you want to look at your data. So like, sort my transmitters by dipole length. Like that I think would make sense in the data class, because that is, we're acting on a SimPEG object and we're acting on a SimPEG data object. But a lot of the IO and parsing and stuff like that, because it's so custom, and once it's in, like you don't need any of that functionality anymore. I think that should stay as a util.
Yes, if you have the IO that reads the file that have like more information needs that you need for the simulation, the survey, the data class. You can as you're reading the file, you can add an options so that what you're outputting is not only the survey and the data, but you also output like some on that database that contain all the information from the file that you didn't need for the data.
But I kind of like the idea of what Mike said, because I'm just thinking about the situation where I do the DC inversion, let's say. I don't have that much information how bad the data are. And actually, you're getting the idea after you do the inversion, like, okay, this portion of data is wrong, and that portion of data is wrong. And then, okay, how do I know that? And those supplementary information is actually important to know. And then, like, the old indices that we've already generated, that's actually really useful to see how those are look like.
Yeah.
So I think those information should be like somehow, if you want to use that, the indices or like how we're parsing this out, like which is in the data class, I think that information should be in the data class. So I was just curious, like how are we going to manage that? So currently we're actually putting everything on the outside and do all those analysis on the outside. So we actually do the things twice, right? Like we generate all the indices in the outside and like do all the analysis and then.
Well, okay, so I think maybe I wasn't quite clear. So I think that like actions that you're taking on the data object, once it's already in SimPEG, so it's in SimPEG, it's a SimPEG data object. And if you're doing a DC survey and there is, like, you want to sort by dipole length,
right.
I think that's fine to have in the data class.
Right.
I think that like bringing in, if there is metadata, we can have like a place to put some structured metadata in the data class. I think that's totally fine. I just don't think that the parsers, like the communication piece that says, let's take this file and put it into SimPEG data, that should be self-contained and not attached to the data class.
Could create their own.
The utility, right?
You guys could have their own data class.
Yeah.
When we import our own, create our own data object that inherits from the base.
Yeah. Yeah, and I mean, if they inherit from,
Or when we form the data class, we just kind of specify like what headers we're going to have
That's right.
basically for our different data columns. So just have like the data object be this pretty flexible thing. So like it requires like a minimum number of, like it requires your observed data and maybe your uncertainties to set up.
so,
Or
okay,
maybe,
so
maybe it just requires your observed data to set up. Like it
Yeah.
requires your survey and it requires your observed data. And if it has those two things, those are kind of like the minimum things, but then you could also specify kind of whatever other data columns you wanted. And you
So I
could have
think
those
one
part of it.
thing that's to just like be a little careful of is like SimPEG doesn't think of data as like an Excel spreadsheet or something like that. Like we don't think of sort of X, Y, Z data. So that's just one thing to sort of keep in mind.
So it's not storing diobs as a vector.
The source diobs is a vector, but it's a self-contained vector, right? It's just a vector.
Right.
And then we index it by saying these are the sources and receivers associated.
Well, I thought you said you were putting it into the dictionary.
It's be a lot more disordered, right?
Well, we build a dictionary based on the survey that keeps track of what indices in the data vector belong to which sources and receivers.
So the dictionary itself doesn't actually contain diobs.
No, it just contains
Yeah,
integers.
okay.
Yeah, it just contains integers saying that like this index is associated with this receiver. And so you can use the exact same dictionary on your uncertainties, right? Because your uncertainty should be in the same order as your diobs.
And if you have an IP decay curve then with multiple time channels, that's still all handled straightforwardly.
Yeah, because then in that case, instead of your data being a datum associated with the receiver, it's just a time series.
Okay.
No, that's fine. Yeah, so like Mike, if there's extra sort of columns that you want to bring in, think of that as a different property on the data class.
Right.
And so all you would do in that case is then inherit like the DC data object and then add a new property to it. And if that's general enough, if that's something that we really encounter in a whole bunch of places, then we'll bring it into the core DC data object. And if not, then like it'll just be a custom data object for your given data set.
Right.
Does that make sense?
Yeah, I think that gives you all the flexibility.
I guess the only danger is that if you create your own data object, right, your own properties, you try to operate and do some operations on another DC that doesn't have those properties. That's fine. For instance, if Mike creates a routine to look at time on the DC, and then tries to do that routine on the regular DC data, that will.
Yeah, so like, and that's just where like, as you're developing, you just sort of have to think about like, okay, is this general enough or useful enough beyond my specific case? If yes, then bring it in the core. And if not, then we'll just build carefully around that. Yeah. There's a few other things I can show. I'm just debating what's most useful. So most of this, like the actual simulation, is quite similar. See, actually, I think sources.
So Lindsay, this class is called new FDEM. Is this something supposed to replace O1 or just kind of keep the two at the same time? Or?
This will replace the old one. We'll probably go through one iteration where if you want to use the old one, you can import old FDEM as FDEM and have it function as it did before. But eventually all of that code is going to get depreciated.
Okay. So the new FDEM was built basically after the change of framework, right?
Yeah.
Okay. All right.
So this is sort of the first crack at the new larger scale sort of simulation.
I see, gotcha.
Yeah. Let's see. Yeah, I don't think much of that was worth going through. One thing I wanted to just like briefly touch on and make sure that it's sort of clear to people, because this is going to heavily sort of require that, you know, heavily, but this implementation is going to require that you're doing inheritance sort of properly. And what I mean by that is that, or why that's going to be important is because there's a lot of sort of steps, each of these properties here that we implement on a class. That's actually something then when we serialize the class, so when we go to either save it, if you want to sort of save that object to disk, or if you want to pickle it so that we can parallelize it, these are the pieces of information that get saved. And so when you inherit from the base class, we also inherit those pieces of information that get saved. And so here, when I'm doing an instantiation, this one's a couple steps because I'm trying to be kind to people when we're renaming stuff. But this is really the important step, is we're instantiating on the parent class. So super just says, call my parent class with the instance of self, so with the instance of this guy. And then we're going to instantiate it with these keyword arguments. And so what that's going to do is it's then going to go, okay, what's in the base FDEM source? So here, my base FDEM source is the survey. So it has frequency and it has a receiver list. And so it's going to bring those objects with it. So you don't need to re-implement these. And as much as you can, try not to, because we'll be able to put things like validators on each of these classes so that I know that for a frequency domain source, just trying to come up with an example off the top of my head. Don't have one. Well, for example, in the simulation class, for a base simulation, a base frequency domain simulation, one of the things that we could do in a validation step is make sure that your padding extends far enough, or your lowest frequency. Like those types of things. So, yeah. But if you overwrite these properties and don't actually do them as properties, then you lose all of that functionality. So when you're building, try and inherit and use the functionality from the base, and then only re-implement if you really do need something different to be happening. And so we can deal with that on a case-by-case basis. But does that make sense? Do you guys have questions about inheritance, stuff like that?
But that's good. But what I'm like worrying about is, let's say you got a base EM class, a whole bunch of stuff, and then you have some problem which inherits that,
yeah.
And then like it barely used like all of those, but it used some of them. And then when I'm serializing this small class here at the bottom, like, am I actually serializing all information?
No, you'll only be serializing what's set, and so that's an important thing to keep in mind. Is that whatever you need to recreate a class. So here, in order to recreate a reasonable frequency domain source, I need a frequency and the receiver list can be empty, so I don't actually need that. But we do need a frequency. This is required. So it has to be a property that we serialize because I need it to recreate the class. If I had something else here, like location, for example. So if we actually provide a raw vector source, I don't need this, right? And I'm not going to set it. But if I have it as a property here, right? If I go and serialize a source that doesn't have a location, that just won't be serialized because it's not set. So hopefully if you're using, like, hopefully if we've done the inheritance right, you're not bringing too much baggage with any object, but yeah, if there's little things like that.
I think that's fine. So what happens actually, like if you go back to your Jupyter notebook and serialize your simulation class, how do
Errors right now, because I probably don't have, yeah, I haven't set up all the properties correctly. But if you look at, I'll show you an example from some of the casing stuff that I've done, because I've saved serialized objects there. So if we go here, okay, so this is my mesh parameters that I've serialized. So I've got HY, sorry, it's not. So it's not nicely spaced, but it saves everything that I need to recreate my mesh parameters class. Or if we do, actually this will work. If I do mesh.serialize, tested. So it saves which class it is. It saves the number of cells in each dimension, because I do need to know that to recreate the class. The Cartesian origin, because this is a cell mesh. And then my H spacings. And that's it, because that's all that I need to recreate the class, right? To build all the operators and stuff like that. That's all from these pieces of information. So.
Lindsay.
Yep.
Is it possible to have the serialization version aware?
Version aware? Yes. I've done that on my casing stuff. So then all we do is just on the base add a version property that grabs SimPEG's current version, which is a good idea.
Yeah, I think that would be very slick.
Yeah. Because especially if names change or things like that.
Yeah, I think it's important too if it's, especially for the saving part of things, because you could have different versions, and then you could think about extending deserialization to actually be able to read old versions into a new implementation.
Yeah, absolutely. Any other questions, or do you want to take over and give us a tour?
Well, I have a question first.
Yeah, sure.
I saw that there was some discussion about it, but the negative for the depth on the deobs file, or on the observation file, is, so I downloaded SimPEG on a computer, a work computer, and it was complaining about stuff, and then I went and got the spectral IP version of yours, and it started to work. But then I was remembering, oh yeah, there's something with this negative depth value. So I'm trying to build right now just a DS class or data class that will just send off an observation object for you guys, or for SimPEG. Is it going to be negative or not? Like, which was it decided?
I think it's positive.
We're just going to keep it positive up? For that? Okay.
Yeah, Z is always positive up. I think the issue with that was just there's one UBC code that we're interfacing with that we're not sure what the sign convention is from the UBC code.
Okay.
But because like the DC UBC code, like the inside machinery in the mesh are Z positive down, but the input file for the data are Z positive up. But we they are Z positive down, so we need to multiply by Z. But the data is not the same. The data file is not the same conversion as the code itself. So that's
okay. Okay, cool.
So it's like the data file from UBC is Z positive.
So, okay.
Yeah, there were a couple things that I had to change to handle the data set.
Yeah.
before we were assuming like one source type has only one receiver type. Let's say if you have a dipole source, then you always have either pole source or dipole source. But it seems like your data set have sometimes a dipole or pole. So even for a single transmitter. So
weird. They should be all dipoles, but just different size dipoles is what it is.
Yeah, I'm not sure why, but that was what's happening. So I had to. I had to let the receiver, like inside of the code, receiver, like let's say, just if you set the dipole, even if that's set the dipole, that's the same location, just change to change.
Oh, okay.
Yeah, I wasn't sure. I was just trying to ask you, like, okay, what is that? Is there actually a case where you either use both receiver dipole and the pole for this?
Oh, well, it should have been just dipoles. Yeah, there must have been something funny in there. I'll have to take a look for that. But yeah, there should be all like a pole dipole. There should not be a pole in there per se.
At the same time, it doesn't hurt to have that generalizability.
Yeah, exactly. Whatever
receiver associated.
Okay.
But with respect to the name, so Z, positive up.
Yeah.
Elevation with Z.
With Z.
Depth, the word depth is usually
down.
Positive down. So
yeah,
just to try to remember all the confusion of that.
Good point.
Yeah, SimPEG is always Z positive up.
yeah. So
yeah.
That's your choice. Like,
yeah, you do what you want. Z's going up.
Do you have? It's all USB-C on these
HDMI, or you can drive on my computer. That's really fine.
If
Goodney, did you get a chance to look at the stuff that John had on his?
I don't think.
That's the real small one on here.
And then what's your?
It should be just.
Goodney, are you still there?
Oh,
Yeah, I'm still here.
oh, okay.
Did you have a chance to look at the processing codes that John had put up?
I did have a
There's
bit
not
of
much
a
there right now, but
look at it. Yeah, no, it's missing quite a bit of components. So, but I haven't had time to do much more than that. I guess we'll have to kind of look at a plan of kind of trying to populate those and add in the necessary codes that are for the processing.
Did you have any? Did you see anything there that was also what you use?
Yeah, I mean it's all there, but it's missing. I mean, it's only getting to the kind of to the Fourier, and then it's missing all the kind of specific things to the MT data. Kind of taking the Fourier coefficients and actually making them into the MT data. At least I didn't find it in this on the Git, but again, I didn't spend a whole lot of time looking.
yeah, it's pretty bare right now. Just kind of put up what I initially had for just stacking DC time series. So yeah, there's no Fourier analysis yet, but yeah, I'll come in due time. Work got a little hectic and I was on vacation too, so. But I got like a basic structure here. Take it through. I think we were discussing in this originally. We'll just have whatever kind of windows you want for filtering. You just get this, make that. They're just all methods or functions, I guess. In a sense. Oh, okay. So numtaps is just. I guess it's kind of a force of habit, like a lingo that we've been using since university. It's just like. How many points really? When we would plot them in school, we plot them as taps, and it would just be like a stem. So you would just have it would be a line, a point, a line, a point, and then you would just.
And so you're using that to say, oh.
So you put how many tabs is you find out how many tabs by how many half periods that you have.
Okay.
And we could definitely name that.
I'm just like trying to get a mapping of what that.
Yeah, so the tabs are just like a representation of how many half periods you have in your signal.
Okay.
Because you're creating your window accordingly to how many half periods you have. So yeah, that's taps is just referring to, yeah, you'd be like, I think it was a MATLAB command, it'd be like tap this, and it would just plot it up. I think that's where that came from. So right now, yeah, I've still needed to report over this code from my C++, but yeah, we got Kate, Kaiser, Hanning, Chevy-Chev right now, and if anybody has ideas on any other ones, just throw them at me and we can throw them in there. Another function, just if you have, so after you've stacked, you can throw your stack into get primary voltage, and you just tell it wherever you want it to calculate the voltage over, and it'll return your VP back. Load DS, I think this is where I was trying to make, I don't know, this is just specific stuff. So yeah, I'd put up some files if you just wanted to load the file into a nice little data structure. The data structure for the DS is exactly what's in the header. So it'll be like load DS, it'll give you an object, it'll be like DS dot VP error dot in error dot current, whatever all the titles are, that's just how you can access them. And then, so I was thinking we'll call just name it right out, the DC or DCIP time series. This will be like the general class that I'll form for whatever kind of data that you want to load in, be it DS or GDD, wherever you get the data. It'll end up making this as a general class. And then, yeah, I'll populate this with what we need. But I'm not too sure much more you need from just the time series. Just really want the time-based sample rate data. And then, yeah, then you can just tell it how many. So I guess some statistical stuff. How many periods you have, how many half periods. Help you make your windows in this. And then, yeah, just this is my first crack at going at brute stack. So this is one of my older codes. But yeah, it's pretty efficient. It was written right in NumPy. But this one just uses it doesn't use a window. It's just like your normal stacking filter. It's just kind of like a boxcar, except for the two ends. A little bit beveled. But yeah, it throws out a stack if you're just looking at high series and just want to brief look at the amplitudes. And then this is the one I'm working on right now. This is my fast one. This is the one that I use for our code. I'm about halfway done. I found some refactoring I wanted to do. I was like, yeah, maybe I'll change this. But I should have that ready by next week. Here. And then I've started in with ensemble stacking. So once I get the normal stack going, this one won't take much longer because I'll just have to break it into ensembles. The stat rejection will take a little bit of time. But yeah, so there will be those three methods available at this time for you guys. And then this is just, yeah, old stuff that I had for loading DS file. You guys wanted to see it.
So the data is just a vector, or?
Yeah, it was, or wait, where's that? Sorry.
If you go up, like for the stacking map.
Oh, stacking here? Oh, sorry. We'll go to like this one right here. Yeah. Oh, wait. I don't think I wrote that right. Yeah, so that should be taking in, yeah, a vector, which is just the time series.
Right.
But.
And then,
oh, sorry. No. Okay, I'm looking at this class now. Okay, so you make this time series, and this time series has a method that if you want to stack it. So if it's just, yeah, you'd be like.
And how you're handling this? Because let's say you got 100 locations.
Yeah.
Receiver. Can I put all of them here in one class, or like each one has a separate class?
Each one would be its time series class, I guess. It would be an array of classes.
Right. So like each point has a class.
Yeah.
Right?
Yes.
And then that's okay.
And then you can operate on that. Right. You can stack it, or yes, get any statistical information that you want. Yeah, we'll just add methods to that.
So on top of this, you may have another data structure where you've got all the locational information.
Yeah, so this would go into something, I guess, similar to survey.
You're passing
or
one
data.
point and then doing like whatever filtering or
an operation on it, yeah. Yeah. That's how it is right now. I'm totally open to suggestions.
Well, just asking, like how does
Oh, for sure. And I'm just, putting forth, I'm totally flexible. So if you guys see something that's more efficient, by all means, let me know.
Then the output of that is like a kind of a 10 time challenge or something? Like
It'll be like say for 2 seconds, it'll be a at 150 samples a second sampling rate. We'll end up with like 600 point vector, which will just be your.
So it's like a flow chart. So you do this stat with this class. You have another class that say now you need to do a time window or something.
Well, actually, yeah, I guess that's a good point. Yeah, so what this is doing right now is it'll just give you that vector, which is the stack, and then you would have to, feed that stack into something else to get, say, your IP windows, per se, yeah. So yeah, maybe that should be rethought so that you're not always just passing.
Yeah,
things
I'm just
around.
curious how you're kind of tracing that up, because like, okay, now you've got a really long time series.
Yeah.
Not sure how many samples you have. But it, like with this process, you're gonna get much shorter time sample.
Yeah.
With some time and a value.
Yeah.
Then you're gonna do another step. Then you might even narrow it down to 10 time channels or something. At the end of the day, right? Like your output is power chargeability, for instance. And even like that could be at 1 point. Right? So how like you need to kind of store some minimal information, at least like which time channel it corresponds to. For instance, and how that's kind of how are you kind of tracking that?
Okay, so that would be like kind of like your next step, because you're talking about extracting, your decay, for example. So right now, that's not really like what I was going to do is just have a method that you feed it this stack, and then you feed it your channel time windows,
right?
And then it just returns whatever your channel time windows, the length of your channel time windows. So if it's just 1 point or one window, it'll just spit back one. But to work that in, so that maybe you're not just using into one nice package would be nice though.
One thing that might be interesting to look at, and we talked about this when we were originally thinking about processing, is to use the ideas that we have in the mapping class.
Okay.
And so what's kind of interesting about that is like, because each of these steps is like, in a sense, you can think of it as a matrix operation. It isn't, but you can think of like, okay, so we've got a vector of this size coming in and something of a different size coming in. So there is like a defined shape to the process.
Yeah.
And so what we've done with mappings is you can basically compose all the steps just with a multiplication. So here, if you wanted to first apply a filter and then stack. So let's do 2 steps. So maybe you want to play with that, fiddle with your parameters, choose the correct window that you want to do on like one data set. We do those things independently, and then you can create a mapping that's just the composite of those 2 functions.
Okay.
And so.
Sorry, what do you mean by like you're bringing them together?
Well, so all it does, like, it's sort of the idea of building pipelines. And so we're saying, like, what I actually want to do in my processing flow is do this first, then do this. Yeah. And so there's some validation that can happen. Yeah, so we set them up, but we don't actually take any action until you actually then say, okay, here's my processing flow. I'm going to call it processing of my data. Yeah. Or times my data, or whatever. And then it'll just go through the pipeline. Okay.
Yeah, I like that.
So that's something to think about. Because what's nice too is you can then do some validation steps in there, and then we also can save like a log, I guess, of your processing, or like properties, like what we were showing with the JSON. Is just save then like the parameters associated with my processing as a simple JSON.
Okay.
And it would save the whole train.
Cool.
Yeah, I think that's definitely the way to go.
I think we could build that, and we could do quite a bit of cool things. Like, well, not only just forward, we could actually think about going backward. Yeah. With like some optimization.
Yeah. No, that's cool for sure.
Yeah, I can
work towards that. Yeah, if you got.
Well, I mean, and there's like everything that you're doing here is not hard to translate to that idea. It's just sort of making sure that we're thinking of each option as a self-contained mapping in a sense. We're taking a vector and translating it into something else.
And it gets this
smaller or shorter or whatever.
Yeah.
Yeah.
So it's just making a system really. You got your input.
Yeah.
And it just your end result output.
Yeah. Yeah. I'll show you just like
Yeah.
quickly what the mappings do. Yeah, so like eventually this will be more on properties, but it is. But in this case, it takes a mesh or a number of parameters. Because we were thinking about initially a lot of the mappings, go from some space onto a mesh.
Yeah.
But we have in between mappings that don't necessarily, so it doesn't require it. But we do need to know how many parameters it has. And then it has a shape, so we know what's coming in, and then the size of whatever is going on.
That's usually.
Yeah, and then this one is simple. It's an identity map, so you get the same thing back. Yeah. And then potentially an inverse and a derivative. But then what's interesting is this guy here. And so this happens when you then compose maps. And so in SimPEG, we do that with a multiplication. So for example, if you are inverting frequency domain data and you just want to invert for 1D exponent or log conductivity below the subsurface.
Yeah.
In order to model it, we need real conductivity everywhere in our domain. So you'll develop an X map, which takes log and translates it, and then we have an inject air cell map. So you have those two steps, and we're going to multiply them together to go from log conductivity below the surface to conductivity everywhere. And so all this guy does, like when we do the multiplication, I think that should be on the base. Yeah, so when we do the multiplication, so if I multiply two maps together, what it's going to do is first check the shapes and say like, hey, is this actually a valid thing to do? Because I know how much is coming out here, and I know what size should be going into here.
So like in parallel, it would be like your time series length coming in, and then you would know your stack coming out.
Yeah.
Exactly. Okay.
Yeah, exactly. And then, so if you're going to then do an operation on your stack, you know exactly what size it should be coming in.
Okay. Yeah.
So here, the first thing we do is just make sure that it's same.
Yeah.
And then the second thing we do is build a combo map. Otherwise, if we're just multiplying by a vector, we actually then just perform the mapping. So we're sort of like, it acts like a matrix in the sense that you can multiply them together and you can multiply them by a vector, but it's not actually necessarily
an actual matrix. Yeah.
So here, when we do a combo map, all this does is just like, as I said, it sanity checks to make sure the shapes are reasonable above. And then here, it just creates a list and then basically says, like, perform these operations in order.
Okay.
But what's potentially interesting in a processing flow, and especially if we start looking at things like X-array or some of these more optimized packages that have really thought about, like, let's build up a pipeline and then efficiently compute on it.
Okay.
We could potentially play with some of that sort of stuff at this level.
Nice.
Yeah, so like here when we do the transform, it just loops over it.
Okay, I like that. That would be great, because then, you say you want to do, give it the pipeline, put it through the pipeline that you want these channels, and those channels you can output, 10 different channel types, and see which one's good.
Yeah, and then saving it and all of that.
Yeah,
so that you can
awesome.
Reload your pipeline later is also done.
I can, advocate for that.
So this won't be like set up for you to inherit yet, but that's something that we can work on.
Yeah? Okay, cool.
Yeah, but probably having an example would be great, but at least even just two, let's say you got this next channel. I'm not sure what else you need to do with them. At the end of the day, you're going to get, let's say, in-time channels for certain window.
Yeah.
Then I think now we got at least 2 steps. So we can
Yeah,
know
that's another
each one as a node, and we can use that using pointable maps
To create the.
And I think the ones that actually works, it's really extendable for a whole bunch of other steps. So
Okay.
that might be
Yeah. I think so. Sure. And yeah, that was pretty much it. And then at the end there, at the bottom of the page was just, I was starting just the DS, like take the DS data and output the SimPEG object.
Survey right now, I guess.
Oh yeah, sorry, it outputs survey, yeah. The depth might be wrong though. I might have changed it when I was moving that the block over there. Then secondly, I've got the big data set there for Arrow.
Oh, for the Saskatchewan.
Yeah, for the Saskatchewan there. However, we've been clocking it at about 156 gigs of RAM needed. So it does need a bit. And if there's no access to that. Glenn was talking about you guys maybe just making a general login. You guys want to play with it at all? We can give you access to.
The 160 gig is actually is it the raw data or the processed data?
That's on the RAM, like just while it's inverting. Bring it all in. Yeah, I don't know. Like when the inversion is running, like after like the first 2 iterations, we just checked how much RAM was being used, and yeah, it was 156. So that's
okay. Oh, I see.
Yeah, that's on board.
I'm asking like just the size of the data.
Oh, the size of the data, yeah, is only like maybe a couple hundred megabytes or something like that.
Oh, so you're running the SimPEG?
Oh no, this is the UBC code.
Okay.
It was at 156 gig. Yeah, sorry.
No, yeah. Okay. So the data is not that big, right?
Yeah, it's not that the data is that big. It's just to set up the problem and everything. It takes a lot of RAM.
Oh, that's fine. That's part we can.
You can do better.
Yeah, right on.
But the data is 156 gig. That's a big problem, I guess.
But yeah, we've got enough on our machine. And Glenn seems to be open to the idea if you guys want to use those machines.
That would be great.
Okay, I'll let him.
But I mean, like, do you have a data set to work with?
Yeah, that's the thing. We have the data set. It's just like I can give it to you, but is there much to do with it? Like I can definitely post it, but if you need access to.
Well, I think we should have the data set. We can do some things with it.
Okay, I will hand it over here this afternoon. I'll just give you a message, or if I can just post it. It is a couple hundred megs.
That's
Does it
fine.
really matter?
Slack should take that, no problem.
Yeah, it doesn't complain. Okay, I'll just post it then. Yeah.
You're on Tensor.
Just a tensor mesh. Yeah, I think there's a push to start playing with like the Octree stuff and whatnot, but just have at the data if you want.
Well, in general, how big is the area? How many electrodes you have?
Actually, unfortunately, I don't quite remember, but it is rather large. I think there should be at least 5,000 injections, I would say, at the very least, on this data set, and each injection probably has upwards of 2,000 dipoles per injection. I think it's probably around, it's kind of 2 offset 3x6 grids, like 3 kilometers by 6 kilometer grids. They're just kind of offset a little bit. So yeah, it's a pretty decent area. Pretty decent size. I think it's 490,000 data points. We got it down to.
And what's the electrode spacing and the cell size that you're using under?
I don't remember the cell size that she was using on the inversion right now, but the range of dipoles go anywhere from 30 to, I think it's around 400. We did I made an algorithm that does like a smart dipole sizer. So if the nodes are farther away from the injection, it makes a bigger dipole. So yeah, it's going to vary around from anywhere from there. I think in increments, it was 30 north-south and 60 east-west for the spacing of the nodes.
Did you say there's 2 grids?
Yeah, it's 2 grids. So it's arrow north, or the original arrow, and then the arrow south that was completed last year.
Yeah, because for us, I mean, at this point, just working with one of those grids would be fine.
Okay.
And then, was there one that had something really interesting come out, or was that the composite of 2 of them? I just remember
that was just the first. The first one was where they found south arrow, and because of that, that's when we did the second grid. And yeah, there's some more nice, nifty stuff there. But yeah, I can ask Charlotte to see if she just has the subset. You just use arrow. I think that one is still approximately like 350 to 450,000 data points as well. Well, no, actually that one would be less. Yeah, probably looking at about maybe half as much, 200, 250. Because if I do, yeah, we have so many data sets right now. We have the smart sizer. The one that was used for the south arrow deposit was just collective, like it wasn't sized, it was just between 30 and 400 every dipole. So it's going to be a little bit, it'll be a bigger it'll be a smaller area, but
more dipoles.
But as many dipoles or more.
Did you actually put your smart sizer onto that first arrow just to reduce the number?
That's what we did for all of it, yeah. And that's the data set that I have right now. That would be the combined one using the smart dipole sizer.
Well, maybe that's, I mean, we could probably parse things out then.
Yeah, you can do that
so
too,
we might as well give us the whole data set because it's all set to go.
Yeah, then you have
we can
both of them.
Parse something out, and if there's some reason to actually really look at both of them together as far as
yeah, that's easy enough because that data set's already prepared. I got that.
Then let's do that.
But yeah, it's easy enough to. You just want the one. Pull it out.
Yeah, no, I think you just give us the whole data set that you've already got prepared and make that easy. Yeah.
Sounds good.
How big RAM do you have?
On that computer, I think we have just 250 some, 256. Yeah. I think Glenn upgraded, and then yeah, the drives. It's a special drive that works. I can't remember what he connected it through, but it's a fast-acting like hard drive, or it's kind of like a mix between the hard drive and RAM. It's just it stores like hard drive, but it's fast accessing like a RAM. And then I think we have like 3 or 4 gigs or terabytes on that. So the files, if there's any page files or anything that need to be written, because that's a has ridiculously huge. Backup files or something like that, and he doesn't tell you. We're sitting there one day, and he's like, "Why does this thing keep crashing? What's going on?" And we look at our like disk space is just, and these files, yeah, they're like 4 terabytes or something. And we're just like, "Oh boy!" And that's like, yeah, I think that's saved every iteration. So it's like you always have constantly this like 4 terabytes on, or when you're doing like a huge data set, you got this constantly on there, and it's like,
Wow. One perhaps last update. I know Joe at Colorado School of Mines, he's been working on Octree. And so he's got a fork on his personal GitHub repo that I can share if I haven't already. And he's got the quad tree, some of the basic operators forming, and I think he made some progress on the octree. And he's a very solid C programmer and Python, so he knows how to layer that so that it's easy for us to access. So we're going to connect with him probably next week or the following week and just chat and see where he's at. Because, I mean, he was, like, with initial tests, he's already got 100x speed up on forming operators. Just, like, yeah, because he knows what he's doing, which is awesome. So, yeah, so we'll chat with him and work on getting a trajectory for his stuff to come in. Yeah, which is exciting.
That's good.
Yeah. Yeah. Any other questions, comments, things? No? All right. Thanks, Deacon and Duty, for joining.
Yeah,
Yeah.
can I have one quick?
Yeah, sure.
Yeah, so Doggy and Dom send a draft for the lower lake to you guys through Google Doc. You can take a look.
Oh, did you send the coordinates? Sorry?
Yeah, I send the invitation to the Google Doc. So
Oh, when did you do that?
I just did.
Oh, okay.
I was like, really? Okay, that's great.
Okay, yeah. So we'll take a look at that. Yeah. So who gets to eat your New Year's cookie, Dequan?
Oh, New Year's cookie. Oh, so I have one. Maybe keep it for me.
Okay, we'll keep it for you. Packaged up. Okay. Cheers, guys. And good. Yeah. Do you think there's a chance then? Like, oh, he's gone?
Yeah.
Oh, okay.
Said bye.
Oh, he said bye. Bye. Bye, Goodney.